I think we should be good here now. Let's have a look here. Yep. Alright, it looks like we are live once more. Okay, so welcome back everyone once more to another session where we can go over the AP Calculus free response questions. And so right now we have the 2024, if the camera would like to focus on this, please. There you go. Okay. The AP Calculus 2024 free response questions are the ones that we will be going over here today. Alright, so all 6 of the questions, like before, going through 2 at a time, and we will be going over the answers. Hopefully, I think we're implementing a better way to show how to correct it, but nonetheless, though, it's still going to be the same going through. Okay, so as always, we have all 6 of the problems out here. These will be copied down over to the notebook that we will be going through with all the answers and every step for problem solving. And with that, we'll be able to go over each individual part all the way to the end, and we can definitely see how we score overall. Okay, very good. So as always, any sort of questions can be answered through the chat or through the email over on that left side over there, the labcoatmath@gmail.com, and we should be going right through these problems together. Okay. So with that, we scored pretty alright last time. A couple of mistakes, which does remind me. Let me quickly get my calculator here. What? It's not right here. Where is my calculator? What in the world? Are we doing amateur hour right now? Where in the world is the graphing calculator? Right here. Okay. It was hiding from me in my desk. So, again, the first 2 problems are going to be calculator allowed sections, which will let us go use our trusty TI-83 Plus graphing calculator, and all of which will be done step by step as well through this part. Okay, so with that out of the way, I think we are good enough to start with our first problems here. So, to begin here with problem number 1, we have ourselves a table here. So we have T measured in minutes. And on the other side, it's going to be the function C of T measured in degrees Celsius here. And we go across at 0, 3, 7, and 12. Okay. And we get the resulting amounts of 100, 85, 69, and 55. Okay, very nice. So the question itself has the context that the temperature of coffee two F's in a cup at time t minutes. So t minutes is modeled by a decreasing differentiable function C, where C of T is measured in degrees Celsius. Okay, and then we have for the interval going from 0 to 12, we have the actual whole table there with all the values listed out. Okay, good. So with that, we have everything we need to get to problem A here. This is that they're asking us to approximate C prime of 5, okay, using average of change over the interval from 3 to 7. Okay. And then also make sure to include units of measure. Okay, very good. So, looks like we have all of that put right there together. And so, again, we are using the average rate of change method for finding this kind of a problem. So, because of that, that means that we have ourselves our points here. So, C of 7 minus the C of 3 all over the actual time difference is 7 minus 3. Again, this is a way to approximate C prime of 5. Looks like they already told us that's exactly what they want to see here, so that we get the average rate of change according. So with that, we will then plug in for those values. So it's going to be 69 degrees Celsius minus 85 degrees Celsius. And with the 7 minus 3, that's a difference of 4 minutes. Okay, so we end up with our approximation. We can run this through the calculator without an issue if you really want to here. So for ourselves here, that's going to be 69 minus 85 all over 4. All right, so as shown right there, it's going to be a negative 4 degrees Celsius per minute. All right, those units are very important to be reflected upon as an acceptable answer to this problem. Okay, and so that's how we do average rate of change. Again, it's a change in the y values. It's subtracted, divided by the change in the x values on that table. Very nice. So part B then continues to tell us that we need to use a left Riemann sum. Okay, with 3 subintervals. Okay. From the table to approximate now we have our definite integral going from 0 to 12 of C of t dt. Okay, then they're next going to tell us is that they want us to interpret the meaning of the expression 1 over 12 multiplied by that definite integral 0 to 12 C of t dt in the context of the problem. All right, very nice. So we have ourselves this problem right here in part B, which again we're using a left Riemann sum, meaning that with 3 subintervals, we're only going to be using the 3 points in terms of the heights on the left side of the table. So 100, 85, and 69 are going to be the heights of the rectangles that we have. Then we need to understand what that expression is going to be at the second half of the problem. But one step at a time, understand that we're doing the left Riemann sum. Means that we need to go ahead and start measuring the distances for the bases. Again, it's going to be a base multiplied by a height, right? And all of them are going to be added up together. So because we have those two things right there, it's going to be the base of the first triangle of just a base of 3, because we're going between 0 to 3. And we have a height of 100 with the first rectangle. Add that up with the next base. This case is the distance between 3 and 7. So that's going to be 7 minus 3 multiplied by the height, again the left height between those 2 points at 85. And then finishing it off with the difference between 12 and 7 for the base, and the height at 69 for the left-hand side point between those two. Okay, so that all puts our work together, something very easy for us to throw into our calculator. So starting that, we get the 3 times 100, and then we're going to add that with the next rectangle, which is going to be the 7 minus 0, which is going to be 4, because do that in our heads first. So 7 minus 3, and then 85 on the height. And then lastly, add that up with the 12 and 7, so it's a base of 5, and 69 as that height. Okay, so we get 985 as the total amount. So 985, that's going to be the total amount in the left-hand Riemann sum that we can use to approximate for that definite integral. Okay, but the second half then asks us to continue going from 0 to 12 C of t dt, right? So what does that mean in itself, right? For this means, right, this is the average value of the C of t function, right? As the average value means that you take that definite integral of any given function and you multiply it by a coefficient of 1 over the difference of the two limits in that function. So this means for us is that the expression calculates so again, it's the average value of C of t. So it's average value C of t. C of t was the actual temperature at any given time. So this is going to be the average temperature of the cup from, now we do those limits, right? It's between 0 and 12 on the time frame. So 0 is less than equal to t, less than equal to 12, right? Okay. And that is going to be the second half of that problem there. Okay, so they didn't ask us to evaluate the actual 1 over 12, right? They didn't ask us to evaluate, they just want to tell us what that means once we put that all together. Okay, so part C then is that for the interval from 12 to t to 20, okay, the rate of change of the temperature okay, of the coffee is modeled by, okay, we have this equation C prime of t now is equal to negative 24.55 multiplied by e raised to the 0.01 power times t all over t. Okay, and then this is where the C prime of t is in degrees Celsius per minute as its units. Okay, then it is asking then for us to know that to find the temperature of the coffee at the t is equal to 20 minutes. And that will be our directive right there. Okay, so we got ourselves a pretty straightforward question right here. Again, now they're asking is that we have from a different time interval from 12 to 20, we can get the first derivative equation that's given right there, right, in degrees Celsius per minute. But we need to find the temperature, so the actual C of 20, right, at the 20-minute mark. The main issue, of course, is that the table only extends to 12 minutes on the data points that are given at the start of the problem. Right? So what can we do here, right? We need to know an exact C of 20 value, but we only are given the C prime function. Well, that means we must return to our good old friend fundamental theorem of calculus, such that if we were to then take the definite integral of 12 to 20, which are acceptable limits for the first derivative function, we can plug our first derivative function C prime of t right in there, which, again, according to fundamental theorem, by doing that, we can get the conclusion that we are doing the original function C of 20 minutes minus C of 12 minutes, which this is already given on the table, right? C of 12 minutes is already given on the table at 55 degrees Celsius. So that's already a given point for us. Meaning, if we were to find and isolate C of 20, right? So for C of 20, we can have that isolated as by adding the C of 12 to the other side of the function to isolate it. We get a positive C of 12 added with the definite integral from 12 to 20. Now, for this, then we plug right back in for the C prime of t function, which was going to be the negative 24.55 e raised to the 0.01 t all over t, and then dt waiting for us on the other end of that. Okay, so we can have this plugged right into our calculators, and we add that 12c, which again from the table is 55 degrees Celsius, waiting on that side, and therefore we should be able to get out the C of 20 value. It should be lower than 55, of course, because the coffee cup is cooling down over time, but nonetheless, this can all be thrown right into our calculator, and we can come up with the conclusion that the C of 20 point is going to be equal to all of that. So let's have ourselves do that right now on the calculator. So it's 55 degrees on that one side, adding it with the math of 9. So that's the function integral, right? So it's negative 24.55 times e raised to the 0.01 times the variable of t. We can use that for the function integral operation, okay? But all of this is still divided by the variable of t. Then from there, we will then tell the calculator to evaluate for the variable of t from the limits from 12 to 20 degrees Celsius, okay? So all that looks good. The negative 24.55 e raised to the 0.01 times t, all that divided by t. Yep, gotta make sure everything is done properly in the calculator. History shows that I have made a few mistakes losing out on some points because of not being careful enough on the calculator section. But nonetheless though, we get 40.329 if you round it properly. So 40.329 degrees Celsius, right? And that is going to be at the 20-minute mark for this coffee cup. Makes sense. We have cooled down from 55. So with that, we can conclude that this is going to be the case for that point. Okay, very nice. So with that, we can go over to part D and we can finish off part 1 on this exam. So it says here that for the model in part C, okay, it can be shown that the C double prime of t is going to be, well, actually, I'm running out of space here, so let's do this. C double prime of t is equal to this new expression that we were going to copy down here of 0.2455 e raised to the 0.01 to the t power times 100 minus t, all divided by t squared. Okay, for that interval 12 going to t all the way to 20. Okay, so then they're going to tell us here that we need to determine whether the temperature of the coffee okay, is changing at a decreasing rate, or at an increasing rate. Okay, good. So this is going to be the question itself, right? Again, it's saying that is the temperature changing, right? Decreasing rate or an increasing rate, right? This again means that it's going to be the second derivative of t. Again, are we going to be greater than 0 or less than 0, right? And because we're going over the entire interval from 12 to 20 on the time frame, this looks like something that we need to graph, right? On our side to look to see if we're above the x-axis or below it once we graph it for that time frame. Okay, so what we can do here is that we can then throw that right into our calculator here. So in this case, the C double prime is going to be 0.2455 times e raised to the 0.01. Now we need to multiply it by x though, because we're graphing on the xy plane instead of calling it t. Okay, and so all of this is going to be divided by, not divided yet, no. We still are going to be multiplied by the difference of 100 minus the value of x, all over x to the second power. Okay, so with that, we have ourselves the entire C double prime equation right there. So let's set up our window to make sure that we're doing this properly. Because we're going from 12 to 20, 11 to 21 should be fine. And the y min max of -2 to +2 is good enough. We're just looking for crossing or being under or below the axis because of that. Well, it looks like on this case, we are going to stay positive. We haven't officially crossed the value on the axis itself, right? We can go ahead and look at the tracing here, right? So that if we just follow along, if we trace along this, right? As you can see, we get very close to y is equal to 0, but we actually never cross over to the negative side the entire time, right? So because of that, what can we then say for the change of the rate of that coffee during that entire time, right? So again, we can say that C double prime of t is greater than 0 from that entire time frame between 12 and 20 minutes, right? Okay, so because the second derivative, so the change in the change of the rate being greater than 0, all right? So the temperature of the coffee is changing at an increasing rate from 12 to 20 on the time frame. Okay, so because of that, right, again, we're showing that with the second derivative being positive, the rate at which C prime is moving is going to be increasing. It is getting smaller over time, and so again, it's still a cooling process in which the temperature will continue to fall. But with that rate, we have proven that as such with part D. Okay, good. So let's go over to problem 2 before we go over to correcting our work here. Okay. So looking at problem number 2 right here, it says that a particle moves along the x-axis so that its velocity at time t is greater than or equal to 0 is given by v of t being equal to the natural log of t squared plus 4 minus 4t plus 5 minus 0.2 times t. Okay, so we've got that written out right there. Then for part A, there's one time t being equal to t sub r on the interval going from 0 to t to 2 when the particle is at rest. Okay, again, in this case, which means not moving. So let's see, we have a viewer, Niraj Mantri, saying that try JEE advanced questions. Okay, well, I actually would not know what JEE is. Maybe you can send over some links to the email and we can go look over that soon. Right now, yeah, there's a bit of demand because the American schooling system that there's the advanced placement problems for high schoolers, which we're looking to service at this time. But again, Niraj, if you have any sort of sources you'd like to send over to the email, the labcoatmath@gmail.com, we can definitely take a look. Joint entrance exam in India for engineering. Okay. Yeah, so again, you can send those over because I wouldn't know where exactly to look for that. But again, if you have something you want to send over to the email, we can definitely go and take a look at that and follow up on. Yep. So hopefully we can try to see if we can answer those types of questions on the scope of our work so far. Okay. So it still says here that we are not moving in terms of the actual particle right there. Right? But then from there, it's going to ask us to find T sub r for the interval going from 0 to t sub r. They're asking, is the particle moving to the right or to the left? Okay, and we need to give the reasons for that. Okay, very good. So on that note right there, right, we're looking for the particle that is not moving at a specific time between the 0 to 2 time frame. Not moving, of course, means that the velocity equation, so v sub t, is going to be equal to 0. That's what it means to be at rest. Okay, so because of that, we can very easily go ahead and graph this out. Again, this is still a calculator section on question 2. So we can graph that to see if we get the velocity to cross at 0 at any given time between that. So we have our graphing calculator back here again, and on this note, we can then plug in for the velocity function. That's all listed right there on the top, and we can plug that in straight away. So that's going to be the natural log of the x raised to the second power minus 4 times x plus 5, okay, minus the entirety 0.2 times x. And so that is the velocity function. Set it out right there. We need to make sure our window is set properly because we're only looking between the time frame to 0 to 2 seconds and nothing else beyond that. So I think for this, we're going from -1 all the way to 3 should be good enough for us. So that way we can go and see, again, going all the way to 2, looks like there is one cross on the x-axis. Again, only counting for the ones that's between 0 to 2, nothing else after that fact. So we can go and tell the calculator calculate for us a 0 that we can cross the x-axis. So we choose a point on the left side before crossing, and we choose one that's on the right side after crossing. And those two will then give us the result of 1.427 if we round it properly. 426, I think. Yeah, 426. 426. T is equal to 0 at the time being 1.426. They actually don't tell us the time unit. This is going to be just whatever for t. Okay. And then, right, so this is going to be, right, the t sub r for that. Again, this means that the particle was at rest. The velocity was 0, so that it's not moving in either direction. Okay. But then the next part of the question is that from the next interval, so going from 0 all the way to t sub r, so all the time before we hit rest, are we moving to the right or left, right? They're asking for that direction. We got our first part where we get the time in which the particle is resting. But the next part, again, are we moving to the right or left? This means that, of course, if we're looking at a velocity function, that means we're dealing with the right being that the velocity is greater than 0, or to the left side is that the velocity is less than 0. Okay, so because of that, we can take a quick look here, and we can easily see that for all the parts leading up to that particle going to rest at 0 right there, that it is all in the positive side, right? So because of that, right, because this is the case that the going from 0 to t sub r, right, the particle is moving to the right from 0 to t sub r. Okay, so in that case, we have everything that we need right here to then show all the things that they're asking for on that part, and proving that the velocity was greater than 0 on the graph leading up to that point. Okay, very good. So with that, we can go over to part B. It's asking us to find the acceleration of the particle at the time 1.5. Okay, then we need to show the setup, of course. And so then the next part of the question is asking, though, is the speed of the particle increasing or decreasing at the t is equal to 1.5. Okay, another two-part section right here, which they're asking about this this particle once more. Again, acceleration, right? The a sub t, a of t, the acceleration function in relationship to velocity is the first derivative of the velocity equation, the one that was given to us at the beginning of the problem. And so once we find that, of course, that we need to plug in for a of 1.5 in that case. Okay, we can do this differentiation by hand, but this is still a calculator problem at question 2. So because of that, we can just as easily go back to our graphing calculator and plug in the function for v of t and run it in terms of a derivative. So at least on this calculator, it's the math button number 8 for the derivative function, which will take a derivative at a very specific point. So with that, the natural log of the, we have our variable of t, so it's t to the second, no, that's y. Let's try that again. T to the second power minus 4 times t plus 5, all of that, and then minus a minus sign, 0.2 times t. If I can type that in properly, my goodness. 0.2 times t, there you go. That is the velocity function in its entirety, but using the derivative operation, it's going to be for the variable of t at the point of 1.5. That's the time that they asked us to evaluate that derivative for. So by throwing all of that together, we get an answer of -1 if we round up properly. So that's -1.000 for that question right there. Okay, but because we need to show that actual setup, again, this is going to be the derivative, right? So we take the entirety of the natural log of t squared minus 4t plus 5 minus 0.2t. Again, we're taking the derivative respect to t for the velocity function, and we're evaluating it at t is equal to 1.5. That's what we're telling the calculator to do right here. All right. So by throwing that all together, we get the acceleration of -1 as a result of that. But then, right, the next part they're asking for is the speed of the particle increasing or decreasing, right? So again, we're doing with an issue with speed, right? Speed is going to be the comparison between the velocity and acceleration, right? So because of that, we can confirm that a speed up, right? Again, this is by definition, is that if the velocity and acceleration are both positive or negative, right? So they both need to be positive or negative to be concluding as a speed up, or a slow down is when the velocity is going to be positive, right? And then the acceleration is negative, or the velocity is negative and then the acceleration is positive, right? By definition, if they are the different signs on the actual velocity and acceleration, we get a slowdown. If they are the same side, so they're both positive on velocity and acceleration, or it's both negative on velocity and acceleration, it will be deemed as a speed up. So in this case, we have a negative value for acceleration already at that point. So then we just have to plug that in for v of 1.5 into the original velocity equation. And with that, we can easily throw that right into our calculators here. So we can go and take the natural log of 1.5 to the second power, and then minus the entirety of 4 times 1.5, and then adding a 5 at the end of that, okay, minus 0.2 times 1.5. Okay, so our velocity, again, by just plugging in for 1.5 on t, as before, we get another negative value of negative 0.077 if you round it through decimal places like that. Okay, so that's good enough, right? We have both negatives on the acceleration and velocity. And so with that, we can indeed conclude that the particle is speeding up at the t is equal to 1.5. Again, we've shown with our work that both the acceleration and the velocity are negative, meaning that the particle is speeding up again, faster in the negative direction for that time frame. Okay. With that, we can go to question C here. It's telling us that the position of the particle at the time t is x of t, and its position at the t is equal to 1 is x of 1. So we're using the x as position as a function. So x of 1 is equal to -3. Then it's asking us to find the position at the time is equal to 4. Okay? And we need to show all the work according, of course. All right. So because of that, we have ourselves here the actual 1 point on position. But again, we don't have the actual x of t function, right? So this guy is evasive to us. We don't have that, but we still have the velocity function as stated earlier as that natural log function. So t squared minus 4t plus 5 minus 0.2 times t, right? We have only this, but they're asking for a specific position again at time is equal to 4. Right? Well, what that means for us is that we need to go backwards again, because the idea is that the position function is the integral of the velocity function, right? We need to take a step backwards by removing the time variable, that is, by one step going back to position. What this means then is that our brains should be making that connection that we need to use the fundamental theorem of calculus, because we can show that with that fundamental theorem, we can take the velocity integral from the time limits of 1 to 4 for that velocity function. Meaning, again, according to fundamental theorem of doing this for a definite integral, that means that we're going back to the position of x of 4 minus x of 1. Right? And this is fundamental theorem very clearly written out right there. So by swapping over x of 1 to the other side, we can isolate x of 4 itself, what we're looking for, as x of 1 being added to the entirety of the definite integral from 1 to 4 for the velocity function, the natural log of t squared minus 4t plus 5, all that minus 0.2 times t dt, right? This can be easily thrown into our calculator because x of 1 is already given as a point of -3. And from that, we can then isolate for x of 4 being an actual answer that we can give out to this problem, right? So again, we're going to do all this directly on our calculator, starting with -3 plus that definite integral, and we end up with x of 4 as a result. So -3 starting right there, we're adding that with the integral, the function integral operation on this calculator. So we can go take the natural log of, we can go with the variable of t, so t squared minus 4 times t, that's a y, 4 times t plus 5, okay? And then subtracted by 0.2 times t again, and then we go from for the variable of t, going from 1 to 4. Okay, so with that, we can have all that thrown in together. Make sure we have everything set up right there. So -2.803 if we round it properly. So the position is going to be -2.803. Okay, so that seems to work pretty alright for us. Okay, just keep in mind that a negative is fine. Again, this position, it's just that think of it like on a number line. So if we're behind the 0 mark, we get a negative position. So again, this is just a very good use of fundamental theorem of calculus for us to show how we can isolate for an actual value from a definite integral. All right. So with that, we can go to part D here. It's saying that we want to find the total distance traveled by the particle over the interval from 1 to t to 4. Okay, and then we need to show this setup. All right, very good. So total distance, that's going to be the key word again right here. Total distance, of course, meaning that we need to go and take the absolute value of the velocity inside the integral in order to find that. Remember, being that, again, this is the absolute value. Meaning we take into account all the negatives and swap it over to positive because we need to see just how far the particles traveled altogether, forgetting if we're below or behind the 0 mark on this on the line itself. So because of that, we can then show, if we want to do everything that's inside of our calculator, that we are taking the definite integral from 1 to 4 as listed on the limits of integration right there of the absolute value of the velocity function. So natural log of t to the second power minus 4 times t plus 5, all minus 0.2 times t dt, like this. Okay. So all of that is still in the absolute value that we must remember to put inside our calculators. And so with that, we can get the total distance of that particle that is being traveled. And so let's go ahead and use our calculators to get that answer. So by doing once more the function integral again for this actual problem, but this also means we need to go use the absolute value and bring up the absolute value inside of the calculator. Then we put in for the function, so it's going to be the natural log of t raised to the second power minus 4 times t plus 5, all that minus 0.2 times t. Okay. Again, this is for the variable of t, so again, we're setting up for the integral itself. It's for the variable of t now going from 1 to 4 as its limits. Okay, which it is yelling at me because I did not close the absolute value properly. So minus 0.2t, then we need to close off the absolute value with the right parentheses right there. Okay, so that's one thing you have to remember. Again, absolute value starts with the parentheses. We're going to tell the calculator that absolute value ends right there with that parentheses. So with that, then it will calculate, and it'll take its time because it needs to make sure to flip all those negative signs right on over. And if you give it just a little bit more time, it would actually spit out an answer for us. There we go. 0.958 is going to be the total distance that is traveled by the particle. All right, very nice. So we have all that we need right here. So we can go ahead and start correcting our work to see how many points we've scored so far on the first two problems. So something that I think I've improved since we've done this before is that I can actually show this side by side now. Let's see if this will show up properly. So if we do this, there you go. Okay. So we have the actual grading results right here, the things that they're looking for. And we can just go ahead and keep up with the actual problem itself right here. All right. So starting with problem number 1, we have all that right there. And I'm going to use, right now I'm going to use my blue pen over here to start doing the corrections to start marking up what they're exactly looking for. Okay. So starting again, this is problem 1 with that table of the coffee that's being cooled down right here. So at part A is that they want us to show the actual approximation right there, right? The C prime of 5. So when we try to zoom up just a little bit more, there we go. Okay. So with the C prime of 5 as shown right there, we need to show that work as C is 7 minus C of 3, 7 minus 3 like that, which is exactly shown right here. So that's exactly what they wanted to see on our side right there. Then ending up with negative 4 degrees Celsius per minute. That is the units that they need to see reflected on that as well. Okay, so because of that, because we showed the work and the units, we get 2 out of 2 correct on that part. I wonder if I need to still change my... Does that blue not show very well? I think I need to change that. Let's go with the darker blue. I should have one right here. Okay. I need to refill my red pen. But so for now, this is going to be 2... This pen... Is this pen out of ink already? Ooh, it's coming. There we go. Okay. So it's 2 out of 2 correct for that part. Okay, again, we're showing the work for the at the approximation of C prime of 5, and we showed the -4 degrees Celsius per minute units. That's exactly what they wanted to see for that. Okay, let's go over down to part B over here. So it's the left Riemann sum, right? So we need to show the actual form of all that being added up together, right? So it's going to be the entirety of the 3 minus 0 multiplied by the heights, again going all the way down. So we did exactly that on our side here with our left Riemann sum. That line of work was exactly what they want to see, right? By the base multiplied by each of the left-hand heights with a total of 985. That's exactly what they ended up here as well. And then the interpretation, of course, of that expression of the 1 over 12 multiplied from the 0 to 12 interval of C of t dt. That was indeed going to be the average value, right? In our case, is going to be the average temperature of the coffee from 0 to 12, right? That's the wording, right? Again, average temperature of the coffee, right? Going from 0 to 12. That is what they wanted to see as well. So with that, looks like that's all 3 points of part B being answered properly. So that will be 3 to 3 correct on this part. Okay. Then going over to part C over here, moving down, is that we have ourselves the actual rate of change, right? From 0 to 12, not 0, sorry, 12 to 20, where we have that C prime, again, equation that they threw right at us over there at the start of the problem. So what they wanted us to do is that we needed to find the actual temperature C of 20 as a result from that first derivative, right? So of course this means that we have to use the integral, definite integral of the C prime function using the fundamental theorem of calculus to then show that we are going from 20 minus 12, right, as the two results of the definite integral. And by throwing that off to one side, again, by moving it over as shown on the problem, again, we needed to move the C of 12 to the other side to isolate for C of 20 right there, right? And that was shown right there on my line of work, that we do end up with the value of 40.329 degrees Celsius. That is indeed the ways and the points which they all wanted to see for us to get full points on this problem. So with that, that's going to be 3 out of 3 correct once more on part C. Then we can move down to part D over here for problem number 1, is that we have now that second derivative, so the C double prime as shown right there, okay, that they all threw up for us from the 12 to 20 mark. So we need to show that the actual looking at the change of the temperature of the coffee is going to be increasing or decreasing at that time frame, right? So we did show that on our graph is that the C double prime of t is greater than 0 from that entire interval from 12 to 20 on the axis, right? So because we were greater than 0 on all that, we did conclude that it is changing at an increasing rate from 12 to 20, right? Again, this is the change of, again, they want, if you really want to write this out, is that this was the change on C prime of t, right? Again, that's why we use the second derivative. So that change on C prime of t is increasing because of that, and our work shows accordingly from there. So that was just a single point there, so that's 1 out of 1 correct. Which means out of this entire part of problem 1, we get it 9 out of 9 for the first part, which is very nice. We can go ahead and mark that down on our packet here. So again, what I like to do at the very front to measure all of our total points here, that we go down for all 6 of them. So 4, 5, and 6. And question number 1 is 9 out of 9. This entire packet will be out of 54 available points. So that is what we start with to begin with on this first part. I think that's a pretty nice start. So let's go over to problem number 2 to see how well we scored there. Okay. So out of 9 points, that's question number 2. Let's go to what we put down here so far. So again, this is where that particle was moving along the line. So starting with question A here, right? We have ourselves the actual velocity at the time in which it crosses the 0. Again, so they want to know where the velocity is equal to 0 because that's what it means to be at rest for that particle, right? So it's not moving at all. So at rest means that the original velocity needs to be equal to 0. On the graph, we did find it to be the time of 1.426. So that's exactly what they wanted to see as the right answer. And then because of that, the entire time frame before, so 0 leading up to that time of rest, is that particle moving to the right or to the left direction-wise? And the graph did show that we were above the x-axis during that entire time. So because we were greater than 0 on the velocity leading up to the particle going to rest, is that it must be moving to the right on that time frame, exactly what they want to see. So that's going to be 2 out of 2 correct for part A. Okay, very nice. Going over to part B over here, right? We have ourselves, next is going to be the acceleration of the particle at the time is equal to 1.5 mark, right? And then we need to show if that then is going to be good enough to conclude that the speed is increasing or decreasing exactly at that time. So for us, again, we made that conclusion that the acceleration is the first derivative of the velocity equation. And so by doing that, we actually run the entire derivative. This is a calculator section, so we can throw this entirely into the calculator to get us a derivative at the single point of 1.5, giving us the acceleration of -1. All right, as you can see, acceleration at 1.5 over on the answer side, acceleration being equal to 1 right there, or -1. That's exactly what they want to see for our setup right there. And so because of that, we can then look at the velocity as well, because we need to know velocity on top of acceleration to then get an understanding how speed is working. So because of that, the velocity was equal to -0.77, as shown right there. Right, a little bit rounded, but that's still going to be correct because all we care about is this sign, right? If we can hide that properly. So again, it's going to be the sign for acceleration and velocity at that time. So because they were both negative for velocity and acceleration, we indeed conclude that the particle is speeding up at that time of 1.5, right? So that is indeed another point for us right there to prove that by looking at the signs of the velocity and acceleration at that time, we can conclude it is speeding up. So part B is 2 out of 2 correct for us. Very nice. Then going onwards to part C, they're asking then, is the position, right, at the time they gave us that x of 1 is equal to -3, so they gave us one of the starting points, but we want to find the actual position at the t is equal to 4, so another position as well after that. Right? Again, we're going to bring back to our work that we're using fundamental theorem of calculus, because if we took the definite integral of the velocity function between 1 and 4, it will then be the difference between the actual position equation from 4 to 1. Right? So because of that, we just simply have to isolate the x of 4 being equal to x of 1 plus that definite integral of that velocity equation, which will be thrown right into our calculator, as is shown on the first part of the answer, right? So by running the integral first and keeping up with that initial condition of x of 1 being equal to -3 that they gave us, those are 2 points off the bat which they were looking for. And then by running the entire line of work, we get a -2.803 as what they wanted to see. So with that, part C is another 3 out of 3 correct for us. Very nice. Okay. And then lastly, going to part D, they want us to find the total distance for the particle. Again, as I stated when we were doing the problem, total distance means that you will take the integral of the velocity, but inside of an absolute value for all the negatives to be shifted over to positives for it to be integrated by. So that's exactly what they wanted to see for us. We run the integral and we end up with the total answer of 0.958. Round to 3 decimal points is good enough for them, giving us 2 out of 2 correct on that part as well. Just a little bit of a check for students to understand what total distance really means in terms of integration. So with that, that will give us another 9 out of 9. You got nothing missing there on question number 2. A lot better way to start than we did last time, so hopefully we can finish strong on the final 4 parts. Alright, let's swap back over to the main camera here, and I'll swap back over as well out of the answer key so that we can move into the next part of the exam. All right, so part B, the second part of the exam, looks like once more we're starting with a slope field, so we'll actually do this one on the packet itself, but in terms of the graphing calculator, we are finally done using this. The questions 3, 4, 5, and 6 will not be using this, so we'll put that off to the side as we do the non-calculator portion of this exam. So actually, to begin with, let me go ahead and copy down the question 3 itself, and then we'll come back to this and do the slope field problem. This one I'm not going to copy over to the notebook. That'll take way too long. We'll just do, because it's going to be like a solution curve, so we'll sketch that out and go back to the notebook after the fact. Okay, so let's go with part 3, or number 3 on this exam right now. And to start with, it tells us that the depth of seawater at a location can be modeled by the function h that satisfies the differential equation, and they give that equation as dh over dt being equal to 1 over 2 multiplied by h minus 1 multiplied by the cosine of t over 2. Okay, then it says where h of t is measured in feet and the time is in hours. Afternoon, which that is going to be t is equal to 0 at that starting point, but also we have the point as well that h of 0 is equal to 4. A very nice starting point for us. I'm pretty sure we're going to use that towards the end of the problem, but we'll get there when we get there. Part A will be on the packet. Okay, so let's actually get to part A now. So we have the question copied down. So for this, part A is saying that we have the entire slope field sketched right there, and we need to give them a solution curve y of h of t passing through that point 0, 4. Okay, a slope field, of course, means that we're just going to have to follow the slopes or the changes of the curvature for this part. So going through that point that's listed off right there at the 0, 4 mark, we're going to try to follow those tick marks to show that we're increasing, we zero, and then we decrease after the fact. So we go up, we hit the 0 slope right there at that peak, right, as shown on the 3 on the x part, and then we start decreasing after the fact. Again, it doesn't have to be extraordinarily perfect. The test grade is really just looking to see that you can follow the slope overall, keeping up with a reasonable shape, and then they'll leave you alone after that. Okay, very good. So that is part A really done already. It's really just worth 1 point. But with that, we can go over to part B and get to some real heavy-hitting questions right here. So it tells us that for the interval going from 0 to t to 5, it can be shown that h of t is greater than 1. Then it says to find the value of t for the interval 0 to t to 5, at which h has a critical point. Okay, so then it tells us you determine whether the critical point corresponds to a relative minimum, maximum, or neither. Okay. Yeah, so we just need to show our response according to that. Okay. So because the entire h function is going to be greater than 1 from that time frame, right? And from 0 to 5, h will then have a critical point. Okay? So with that, then we can go and take a look back to look at the original differential equation. So dh of dt is equal to 1/2 h minus 1 times the cosine of t over 2. Okay? And again, critical point means that, right? So using a critical point means that the differential equation is equal to 0. And then we need to go ahead and find the actual results of that. Okay? So because of that, and given that h of t is greater than 1, so this guy in there, right? Because h of t is greater than 1, this will not be equal to 0, right? Because we have those all, the 1/2, h minus 1, and cosine all multiplied together, meaning that we really have to look to see if cosine is going to be equal to 0 at any point from 0 to 5, right? So looking at cosine of t over 2 being equal to 0, right, going back to our good old knowledge of trigonometry here, means that we need to get t over 2 to be equal to, right, either pi over 2 or 3 pi over 2, right? Those will be 2 points in which we will be actually getting to some critical points there, okay? Of course, anything past 2 pi is going to be well over 6, so there's no real point in that, okay? So we have these 2 points right there, right, to make cosine be equal to 0. But then, of course, the next issue is that are we going to be minimum or maximum as a result, right? And given that the h minus 1 is always positive, right, again, because the h is greater than 1 as stated earlier in the problem, then all we need to do is really look at the cosine of t over 2 and do a number-like analysis at the 2 critical points that we were looking at. So pi over 2 all the way over 3 pi over 2, okay? Right, meaning that in that case, t is equal to pi or 3 pi, which you realize, right, if that is the relationship that we're dealing with, right, 3 pi is out of the picture because that goes well beyond the 5 mark in which they were looking at. So because of that, we can kick out the 3 pi over 2, and we're really looking at pi over 2 as a possible critical point for this guy, okay? So looking at the way that cosine operates though, right, is that before pi over 2, we're all going to be positive, and then we go negative afterwards. Again, remember the cosine graph starts at 1, and then we go underneath, right, at the pi over 2 mark. Right, you can use some of that to jog our memory to make sure we understand how the cosine is going to work in terms of this guy. So because we go from positive to negative, this again is going to be for the first dh over dt equation. This means that this is going to be a relative maximum. Maximum at the t is equal to pi. Okay. Remember, that's t is equal to pi to get pi over 2 inside of the cosine. All right, which indeed is going to be less than the 5 as stated before. Okay, very good. All right. So then going to part C here, it says that we must use separation of variables to find y is equal to h of t, the particular solution to the differential equation dh over dt being equal to 1/2 h minus 1 times the cosine of t over 2, okay, with initial condition of the h of 0 being equal to 4. All right, and there we have it. All right, so from there, we need to do separation of variables. Again, we need to get to the original h function back again. All right, so because of that, we get dh over dt being equal to 1/2 times h minus 1 times the cosine of t over 2. Okay, so this means all the h's need to go over to one side, and then the t's need to be going back over to the other side for us to take the integral of both sides of the equation. So this gives us dh over h minus 1 being equal to 1/2 times the cosine of t over 2 multiplied by dt. All right, from there, we will be able to integrate both sides of the equation and work our way backwards, meaning that we end up with the natural log of h minus 1 on one side. Then with the 1/2 as a coefficient to the cosine t over 2, that's pretty nice. That gives us a sine of t over 2, the 1/2 coefficient being handled by the t over 2 inside of the sine function. And then we have a plus c. Very important to have that plus c because we're doing indefinite integration on both sides. So with that, we have enough to then solve for c, that constant of integration, because we have the h of 0 being equal to 4. So with that, we can show that the natural log of 4 minus 1, plugging in for h, as a result of that function point, then going to sine of 0 over 2 plus c, will be written out like that. Okay, so from there, it's going to be c is equal to the natural log of 3, with, of course, sine of 0 going to 0 from that point. Okay, so because of that, we can go revert back to our original function that we're working out right here. So a natural log of h minus 1 being equal to the sine of t over 2 plus the natural log of 3. Then if we want to remove, to isolate for h, because that's exactly what they want us to do at the start of the problem, we will have to raise everything entirely to the power of e, such that the e and the natural cancel, and so will the natural log of 3. So from that, our next line of work will show that we have h minus 1 being equal to e raised to the sine of t over 2 multiplied by a whole 3 as a result of the e canceling with the natural log on that side. Okay. Then, on its own, the h of t function is now isolated by moving 1 to the other side of 3 times e raised to the sine of t over 2, and then plus 1 on the outside. And there you go. We have successfully done our separation of variables to then have h over on one side and the t's all on the other, back to the original equation from the differential equation that we started out with at the beginning of the problem. Okay, so that will do for that. And we'll go over to question number 4. Let me double check something very quickly here. Yeah, okay. Okay. All right. So with that, let's go over to question number 4. And we'll see what we will do on this. Okay. It says here that the graph of the differentiable function f, so yeah, that's right. So f has a horizontal tangent line at x is equal to -2 and is linear for going to 0 to 7. Okay, so then let's go, let's see, let R be the region in the bounded part of F. Okay, so and this is R also has an area of 12. Okay, very good. So let's go ahead and start putting this through here. So we go 3, 4, 5, 6. I think that should be fine. Okay, so we go 1, 2, 3, 4, 5, 6 right there, and then we go up 3. So 1, 2, 3 like this, and so at the 6, 0.5 mark right there, we have one vertical line right there. Okay, then we go to 0, 2, so we get a nice curve going up like this, and then we go all the way down as 1, 2, 3, 4, 5, 6. Okay, and then 7's really off right there. But at 6, -1, we have the rest of the line going straight down into there. Okay, region R is back there as shown. Let me change the colors here to show what that looks like on this side. So region R is this entire bounded side right there. and has an area of 12 as is stated. Right, this is the graph of f. Graph of f as shown right there. Okay, good. So let's go over to part A here. It tells us that the function g is defined by g of x being equal to the integral going from 0 to x for f of t dt. Okay, then it tells us to find the values of -6, g of 4, and g of 6. Okay, very good. All right, so with that, we should have everything that we need to go ahead and start putting this through. So let's see here. So on this part, right, so if you want to start plugging this in, so this means that if we do g of -6, we get the side of the definite integral going from 0 to -6 to start with f of t dt. So the issue is that we don't like going from 0 to -6. We need to swap that over so that we can actually take the proper integral. So by slapping on a negative coefficient, we can flip the limits going from -6 to 0 of f of t dt. Right? Now this can be done easily, right? Going from -6 all the way to 0, right? That is the entire actual region of R, right? All this is just the region of R taking the area. So that's going to be equal to 12 for us to start with. Pretty nice. That's what they told us at the start of the problem for the entirety of going from -6 all the way to 0. That needs to be negative in there. So -6 all the way to 0 on that graph. Okay, that's the first part. The second part is going to be g of 4. Right, so we then take the definite integral, this time from 0 to 4, f of t dt. Right. Also, one thing before we even continue is, well, we have that negative coefficient waiting for us because we swapped those limits. So it's actually going to be -12 as a result of g of -6. Okay, so because of this, the second guy does not need any flipping because going from 0 to 4 is perfectly fine, right? So 0 to 4, again, is going to be that part right there. Okay, actually 4... Oh, I didn't really graph that properly. 4 actually is going to be 0, so that's going to be 4, 0 as shown. It's going to be shown properly on the graph, right? So actually, the entirety of this is going to be a triangle, right? So this is going to be an area of a triangle, as what the definite integral is then asking for, going from 0 all the way to 4, but then the height, right, is actually going to go up to 2, right? So 0, 2 is going to be the coordinates for that point crossing the y-axis. So because of that area of a triangle will then mean we can just take that geometrically with 1/2 times the base times the height of that triangle, right? Base times height, of course, is going to have on this graph a base of 4, right? So it's 1/2 times a base of 4 and a height of 2 going up to the length to that part of the triangle. 1/2 times 4 times 2 is just going to be a positive 4, and that works out pretty nicely. Then lastly, by going g of positive 6 here, right, going from 0 to 6 f of t dt. Okay, what is possible now is that, thanks to our knowledge of how to work our way around limits, is that we can split this up into 2 parts. So we can go from 0 to 4 f of t dt, and add that with going the last bits from 4 to 6 f of t dt. Okay. So with that, we actually can go ahead and look at this if you want to let me swap colors again here, just to show it. So we have our first triangle going from 0 to 4, as shown right. I think I should switch colors. Let's go ahead and I think I should have red ink here. So we have, yep. So going 0 to 4, we have that triangle to deal with, right? That whole entire positive triangle, but we have this little bit now from 6, right? We have this little bit of a negative triangle then to deal with after the fact. Okay. Now with -6, positive 6, -1 as the coordinates, that will be to our advantage here. So this really solved earlier from 0 to 4 with g of 4 before. That's a positive 4. We're going to add that with from 4 to 6 being that negative triangle that's underneath the x-axis. So it's going to be negative, well, that's positive 1/2. The height will be negative. So from 4 to 6, the base is 2, and the height is -1 because we dropped down to a -1 on the y value. So with that, that's just going to be a 4 minus 1, giving us a positive 3 as a result for g of 6. Okay, and that is all 3 points of that found using fundamental theorem and looking underneath the actual graph for our heights and our answers there. Okay, going to part B, it tells us that for the function g, as defined in part A, okay, find all values of x in the interval 0 to x to 6, at which the graph of g has a critical point. Okay. Critical point, of course, looking back at our definitions here, means that they were talking about the first derivative of g being equal to 0, right? And we're only going from the interval from 0 to 6. Okay? Well, if we're looking for the first derivative of g, right, what that will then be equal to is that by taking the derivative, so again, this is going from 0 to x f of t dt, and if we're going to take the entirety and take a derivative in respect to x, well, that means that we have to go back to our fundamental theorem and understand that we're just dealing with f of x by itself, right? The first derivative of g is equal to f of x after that. And just a little bit of fundamental theorem, but that goes a long way for us to then put that all the way through. Okay? So because of that, we can go ahead and take a note here that by looking at f of x, we need to see all the points from 0 to 6 in which we cross the go on the x-axis of 0, right? And the graph, of course, only has one point at 4, 0 of that happening in the first place. So at x is equal to 4, and g of x has a critical point. Okay. And that really is it. That's just the only group. They don't really care if it's a max or min. They just want to know where the critical point is. And because the first derivative of g being equal to 0 is also equal to f of x, we just look back at the graph of x and graph of f and find where we cross that 0, which is at 4, 0. Very nice. Going to part B, it tells us that the function h is defined by h of x being equal from 0 to x of, sorry, not 0 to x, it's negative 6. Negative 6 to x, f of f prime of t dt, like that. Okay. Then it says us to find the values of h of 6, h prime of 6, and h double prime of 6. Okay. And we need to show all that work to get there. Okay. So going one step at a time here, h of 6 is going to be defined by plugging that right in from the function. That's going to give us the integral from negative 6 to positive 6 of f prime of t dt. Okay. So it's not just f of t, it's f prime of t dt. What that means, of course, is that we can go ahead and use fundamental theorem by understanding by taking the integral of a derivative, right? Again, this is fundamental theorem of calculus right at work right here. By taking the integral of the derivative, we can go back to the original function of f of 6 minus f of negative 6, right? The top limit minus the bottom limit. F of 6, now, of course, going back to the graph, f of 6 is negative 1, f of negative 6 is 0.5. So this is going to be a negative 0.5, giving us an entirety of negative 1.5 as a result of h of 6. All right. Then moving from there, we can go with the h prime of 6 being equal to the x from that. Okay. Now, something that we need to take a note, of course, is that we need to go back to first taking the h prime of x first, right? It's back into there. So because of that, this is going to be the entirety from negative 6 to positive 6 of f prime of t. Oh, no, sorry, it's x. My goodness. So again, h prime of x as we're copying down from the start of the problem there, which what is happening? Okay, I think that thing just, we had a little bit of a hiccup there. But going from, again, once more, by doing the h prime of x, right? Going from -6 to positive x, right there, for f prime of t, dt. Again, we can go ahead and go take that first derivative, meaning that this is going all the way back, removing the integral there by giving us f prime of x as a result. Okay, again, this is once more fundamental theory of calculus right at work here on how to take the first derivative of an integral equation. So because of that, by going back, by doing h prime of 6, that's simply just going back to the f prime of 6 and plugging that right in there, right? Okay. F prime of 6, again, this is going to be the actual linear function right there. Okay, so because we actually go from 0 to 4, right? So if you look at the entire line, we go from points 0 on the x all the way to 4, and then 2 all the way down to 0, right? So you have 2 points here which can help us find the derivative. Again, this is just a line that goes straight across, which means we can just do slope equation from the change of the 0 minus 2 over 4 minus 0. Again, the 2 points of 0, 2, and then 4, 0, as was the start of the problem on that graph. So because of that, we get a -1/2 as a result of their slope. And that's what f prime of 6 already is. Okay? Then we can go back here. So we can do our last one of h double prime of 6. And this part now can be described as, again, because we built off of f prime of 6 on the first part, that means we're just going back to f double prime of 6. Okay? So that's what that would mean for us on that part, right? But in that sense, though, the main issue, of course, is that by taking a second derivative, again, that's concavity. And the issue is that at 6, we are just still on a singular line here, right? On a straight line, we have no concavity, right? Concavity, we have a straight line, right? Meaning that the actual second derivative will go straight to 0 for h double prime of 6. Okay, and that's what that really means. Again, just so long as we keep up with all of our definitions, that will be the case here. Okay, so that's questions 3 and 4 answered, and we should have everything we need to start correcting those before we get to our last section here. So let's go back over to question number 3, and let's move on over to our next screen over here so we can follow up on some of those answers here. So let me put this up here, going down to problem 3. Okay, so I'm going to switch the screens over and we can go ahead and see what we have on question number 3. Okay, so we had that question number 3 had this slope field graph here, which we'll get to in a second, but this was the one where we had that differential equation and we had an initial point. So on problem number 3, this was something that we had to do on the packet, because we had that slope field that we drew that solution on. And again, because we had to make sure we go through that point of 0, 4, all we had to do is follow the actual slope field lines, making sure we had that horizontal tangent line right at the 3 mark. And that solution curve is good to get us 1 out of 1 correct there. Okay. And this didn't have to be explicitly correct. Again, it can be higher or lower depending. They don't really care about that. They mostly care about the shape of this graph to make sure it lines up with those slope field lines, which it does in the answer that I have here that we've done earlier. So part A is a 1 out of 1 correct. Now we've shown right there. Okay. Then going on to part B over here, then let's see if we can get down there. So again, we need to show that we have that critical point, right, that they wanted to know for the entirety that h is greater than 1. So with that, again, we need to see if we were dealing with a relative minimum or maximum from that critical point going from 0 to 5. Okay, so because of this, right, we show that through implication here that because we are equal to 0 for that cosine function, which t was inside of, right, the t is equal to pi will then be our critical point, which is what they want us to see. Then from there, right, by using the entirety of dh over dt being equal to 0 as what they want to see right there, is that we can go use a number line evaluation here, right, at the pi/2 mark for cosine of how we will transition. Again, with the cosine function, with a little bit of graphing off to the side, we can show that we're going from a positive sign to a negative sign of the cosine as the t continues to increase beyond that pi mark, meaning that we do have a relative maximum going from a positive to negative sign on the differential equation. So because of that, that's going to be correct as well. So that's all 3 out of 3 correct for part B. All right. Going down to part C here is that we then need to use separation of variables to then find that original function y equal to h of x, right, h of t right there, right, from that differential equation. So we can go ahead and start with our lines of work here, given that we need to show that h minus 1 is moved over to the side of dh and dt is moved over to the side of t. So that separation of variables is what they want to see. Then we run the actual integration on both sides of the equation because both have dh on one side and dt on the other, right? Then on that side, then we can end up with the equation, making sure we have the plus c, right, as the result of indefinite integration. All right. So because of that, we will then solve for that c with the initial point of h of 0 being equal to 4. And plugging that right in there means that we get c being equal to the natural log of 3, right? Okay, so we run that through. We put it back to the original equation once more, again with the natural log of 3 showing up. Then to isolate h, right, on both sides, we have to take the e exponent on both sides to cancel out that natural log. And by moving over that -1 lastly, we get the final result of h of t being equal to that 1 plus 3 times e raised to the sine of t over 2. That is exactly what they want to see. Yes. Tanvir says, hi. Yes, hello. You've caught us in our one of our live streams here, which we're going over the AP Calculus test. We're in the section of we're actually correcting our work based off of the actual answers posted by College Board. So hopefully if you want to say hello to us, yeah, that's really nice of you. And again, we can follow along with all the steps to make sure that our students that are studying this exam will be ready for it within the next month. So with that, we've just finished our separation of variables integration on this part of the problem, which with everything being lined up here, that will give us all 5 out of 5 points for this question. Okay. So with that, this concludes the question number 3, giving us 9 out of 9 correct on this part. So I do like to keep record of that to see how much out of all 6 questions, how we've been scoring so far. And with another 9 out of 9 under our belt, we are halfway through getting a perfect score, hopefully, through all of our responses here. All right. Very good. So we will go over to problem number 4, which we've completed, and we'll see what the actual answer key will tell us here. Okay. So question A here is that from this entire graph of f that they threw at us with that region of R, which was everything before x is equal to 0, with a specific area of 12, we can then use that to start answering the questions of the different points starting with g of -6 right there, right? And remember, we do have to flip the actual integral on the limits because we will evaluate it this time from -6 to 0 instead, making sure we have that negative coefficient. Because -6 to 0 was already defined as r in the problem, right? We get a -12 as a result. Okay. Let's see. We have Tanvir saying that his exam is in a few days. He does physics, chemistry, biology, and other subjects, but not math. Okay. Yes, how indeed can you get better at math? That is a great question from one of our viewers. Well, Tanvir, well, again, as what we're doing over here, math is really a study. I think it's a good mix of memorizing concepts and doing problems over and over again. That really is most of my advice. Again, as the title suggests, this is actually the 12th time we've been doing this since the start of this channel, of going over an entire exam packet of 6 problems, all free response. Again, so no multiple choice, but all free response answers. And so usually for people that are going through math, again, a lot of it is going to be doing problems over and over again because it is a test on concepts and a little bit of memorization on how to answer these types of problems. So again, this kind of way for our students to improve their scores. that's not to say for right now. Usually, again, math is a very broad subject, so there's lots of different classes and different things you need to go over. But in terms of the broad spectrum of it, that's kind of the main way to improve your score in math. So hopefully that helps out for you. Again, any direct problems you can send over to our main email line. Oh, it doesn't show right here, but we can get to that. I'll remember to do that at the end of this corrections here. So let's go through and let's see what the rest of our answers are here. So again, because we have g of 4 as the next question right here, is that we're doing the definite integral from 0 to 4 for the f of t graph. So again, because of that, that means we will actually take the area of a triangle as shown on the answer key, right? Of 1/2 times the base times the height from 0 to 4 as shown on that graph, right? So by doing that, we get an area of 4. Okay, so that's pretty nice. Then going to g of 6 right there, then we go take the definite integral from 0 to 6 for the entire f of t function. Then because of that, going from 0 to 6 means that we can split off from 0 to 4 and then going from 4 to 6. A very practical principle in terms of definite integrals, because we already took care of 0 to 4 earlier. And then we need to make sure we have that negative triangle, the triangle that's underneath the x-axis, going from 4 to 6. And because of that, we end up with an area of 3 right there. Okay, very nice. So this entirety is all correct, giving us 3 out of 3 for that part. Then we can move on to part B here. Right. So part B says that for the function g defined in part A, again, we need to then go ahead and look at any critical points here. Okay, so because g prime of x, using fundamental theorem of calculus, by taking that derivative, we are taking the derivative of the definite integral for f of t dt, meaning that g prime of x in relationship is just f of x. So therefore, if we want f of x equal to 0, we just have to look back on the graph, and we do see that we have a 0 at x is equal to 4. Right, so we both score 1 point on knowing that relationship, that g prime is equal to f of x, and then looking for that 0 is equal to 4 because of that. So then that is all 2 out of 2 correct on part B. Should be very straightforward on that mark right there. Then lastly, we're going to part C here, that the function h is defined by this guy, the 8 is from -6 to x of f prime of t dt, and then we need to find all the values 6, -6, and the double prime of 6. Okay, so because of that, starting with h of 6, we just use fundamental theorem right here to then realize that by taking the integral of a derivative, we can go back to the original f function of 6 minus f of 6. We plug in those points and we get -1.5. That's exactly what they want to see right there. Then for the h prime of 6, we can then realize that by taking the derivative of the integral right there, using fundamental theorem again, is that this is going back to the f prime of 6 line, right? Because we transfer over the x into the actual function after taking the derivative of an integral. So because of that, because f prime of 6 is just on the actual line itself, that just means we do a very simple slope of that line itself, reaching to positive 6, giving us -1/2, as was stated there on the problem. Okay, and lastly, because we're taking the derivative of h prime of 6 by taking one more derivative, realizing that it's for a straight line, that will end up with 0 as a result, which is exactly what they want to see there as well, right? Okay, so all those pieces of work there, coming all the way across here, will give us all the points available at 4 out of 4. Meaning that with everything here correct, that is another 9 out of 9 for us for problem number 4. And that's pretty nice. Okay, so all 4 of them are going to be correct, looks like. So we have one more section to go, and that will really seal the deal for us for this packet so far. Okay, so let's move back here over to our main desk over here. Make sure we switch back over to our packet. Okay, so again, it does show here, if Tanvir, you're still over here, that our main email is labcoatmath@gmail.com. Again, over on that left side right there. I know you're saying that you were struggling in some issues with math, so any direct questions you can send over to that email if you'd like. If you want me to take a crack at it to see if my explanation might be a little bit better than what you're currently dealing with. But nonetheless, though, we have 2 more problems to go, questions number 5 and 6, and we can then see how well we've done on this exam packet. Okay, so again, so question number 5, this will be copied on over to the notebook, and we will be well on our way here. Okay, so question number 5 tells us that we are considering, let's consider the curve x squared plus 3y plus 2y squared is equal to 48. Okay, then it tells us that it can be shown that dy over dx is equal to negative 2x over 3 plus 4y. Okay, so we have all of that coming together right there. Then the actual first problem A tells us that there is a point on the curve near 2, 4 with x coordinate (3). Okay, use a line tangent to the curve at 2, 4 to approximate the y coordinate of this point. Okay, good. So we got a few things to look at over here. Right, so there is that point on the curve near 2, 4, the x coordinate of 3. So we then need to approximate the y coordinate from there. Okay, so because of that, right, we need to use the line tangent, meaning that we need to go to our original tangent line equation, y is equal to m multiplied by x minus h plus k on the outside. Right, we can find h and k based off of the coordinates which were given to us. Right, so again, 2, 4 is in that form h, k. So we plug that straight away through, which means we just need to find m to finish this off. Right, so because we have the coordinates h, k, we can go back to that differential equation of dy over dx, and we can evaluate for the 2, 4 point, right, for the x and y values, because both of them are needed for us to put that into this equation to then find the slope at that exact point. So by plugging in the 2 for x, 3 plus 4, and then 4 for y, we get negative 4 over a positive 19. All right, so with that, we can go back to our slope point slope form of this equation here of negative 4 over 19, x minus h being positive 2, and then k being a positive 4. Okay, so then we need to then approximate, again, we're now approximating x is equal to 3 point. Okay, so that means x is equal to 3 is going to go right into that tangent line equation, and we can come up with an actual response here. So by plugging in x is equal to 3, we get 3 minus 2 plus 4, okay, meaning we get negative 4 over 19 times a 1 plus another 4. Okay, and we have just a little bit of analyzing to do on the actual fractions here. So with the 4 with the 19 denominator, that should be what, 76, right? So it's negative 4 over 19 plus a 76 over 19, giving us a 72 over 19 as the y coordinate. Okay, just a little bit of work here with an approximation using the tangent line equation. Again, all thanks to the first derivative equation that was already given to us. And so with that, that should do it for part A. Okay. Then going to part B here, they're asking, is the horizontal line y is equal to 1 tangent to the curve. Okay, so if we have a horizontal tangent to the curve, what this means that, right, is that y is equal to 1 must make the dy over dx be equal to 0, right? The first derivative equation, if it's equal to 0, that means we do get a horizontal tangent line at that point. So let's see if that's going to be true, right? So if we have dy over dx evaluated at y is equal to 1, we get a result of negative 2x over 3 plus 4. So negative 2x over 7, right? So if we want this still to be equal to 0, that must mean, right, x must be equal to 0 as well to make that entire fraction still go to 0. Okay? Now the question is, right, so if we have the ordered pair of x being equal to 0 and y being equal to 1, right, does that make sense for us? 0, 1 exist on the curve, right? If that's the case, yeah, then in that case, the actual coordinate itself would make the line tangent to that curve. But again, does it exist on the curve itself? That means we need to refer back to the original equation, right? That was the curve itself in that big equation of x squared plus 3y plus 2y squared equal to 48. And let's see if that is actually true for this part of the problem. So going back to the original equation, so x squared plus 3y plus 2y squared is equal to 48, right? If we plugged in from the point of 0, 1, would this still be a true statement, right? So we get 0 squared plus 3 times 1 plus 2 times 1 squared. Is that equal to 48? And by looking through this work here, we end up with 3 plus 2 is equal to 48, which is clearly not true, right? So that point does not exist, right? It does not exist on that curve, meaning, right, that the horizontal line y is equal to 1 is not tangent to the curve. And our work will show for that, right? We find the coordinates that would make that the case, but the actual, right, even though the derivative would lead us to 0 there on that point, the actual x and y coordinates to make that happen does not exist. Therefore, it will never be on the curve to make that horizontal tangent ever touch the graph itself. All right, very good. Then we continue forth that the curve intersects the positive x-axis at the point radical 48, 0. Okay, they're asking, is the line tangent to the curve at this point vertical? Right. Again, we need to show our work for that. Okay, so because we have the curve intersecting the positive x-axis on that point, right, again, is that line tangent going to be vertical, right? So a tangent line being vertical, that must mean that the differential equation, right, at whichever point that we're dealing with, that's what it means to have a vertical tangent line at any given point. Meaning that if we go back to our first derivative here, is that negative 2x over 3 plus 4y, again, this must be equal to the denominator going to 0 for it to be undefined. Meaning, right, that if that were the case, right, y must be equal to there must be the result. Actually, let's take a step back. So that means, again, this means that 3 plus 4y must be equal to 0. Then by taking the proper steps, as negative 3 over 4 being the result on the y. Okay, right? So because we have that point of rad 48, 0, right, do we get the actual point in the curve to be vertical on that point, right? Because y is not equal to 0 at that point, is actually equal to negative 3, 4 to make that denominator of the first derivative equal to 0. That is going to mean that no line tangent to the curve at rad 48, comma 0 is not vertical, right? We can go about the other way too, is that because they gave us the actual point itself on the curve, we can evaluate that on the coordinate as well itself, so rad 48, comma 0, right? We can evaluate that to see what the slope really is for that tangent line, because for that, that's going to be negative 2 times rad 48 over 3 plus 0 times 4, right? So because of that, we end up with a negative 2 over 48 over 3. This is not vertical, right? That is an actual negative slope, so it does come at a diagonal. It is not going to be vertical because we do know what that differential equation will give us for the slope of that tangent line at exactly that point. Okay. Then lastly, it tells us that for the t is greater than or equal to 0, a particle is moving by the equation y to the third power plus 2 times x times y is equal to 24. Okay, so at the instant, the particle is at 4, comma 2. Okay, the y coordinate is decreasing at a rate of 2 units per second. So we have a little time factor here, which we'll keep track of here. Okay, and then at that time, what is the rate of change of the x coordinate, right? In that per time frame as well. Okay, so we've got a lot going on here. First off is that we have y cubed plus 2xy is equal to 24. Again, this is going to be the particle, as well as the fact that with the 2 units per second, that is a y coordinate decreasing, right, at a specific unit per second, meaning that a change in the y value with respect to time now, so it's not dy over dx, it's dy over dt because we're changing in respect to time, is a decreasing rate, so that's negative 2 units per second, right? Now then, because now we want to know the rate of change of the x coordinate, they are now asking us to find dx over dt for this entire equation, meaning that we are going to look like, because it's over dy over dt and dx over dt, that's going to be implicit differentiation, right, that we need to do on this problem. Implicitly, of course, meaning that we're going to take this entire particle equation, take a derivative with respect to t, meaning that that's how we can get dy over dt not going to 1, but going to the actual results of those differentiation. Meaning, of course, we have to take care of chain rule, so by doing the actual implicit differentiation, we run through all the steps here, that it becomes 3 times y squared dy over dt. Again, keeping track of chain rule because of that. Then the 2x times y, that's going to be product rule, so it's 2 times y times dx over dt plus 2 times x times dy over dt. Remember, product rule is very important for us to remember when taking the derivatives of that function. Okay, so with that, it's going to be equal to 0 because 24 is just a constant number. And so with that, we then need to isolate for dx over dt before we finish off this problem, right? So going through here, we get the 2y dx over dt, and we move everything over, so that's a negative 3y squared dy over dt. Now subtracted with 2x times dy over dt. Okay, then we can move everything one last time, so dx over dt is equal to all of this, right? All of this guy divided by 2y at the end to move this guy all the way over to the right side. Okay, a little bit cramped for space, but I think we can finish this off just in time here, meaning that we get the negative 3 multiplied by y squared. So again, we have the coordinate of 4 comma 2 at the start of the problem. So that's going to be 2 squared. dy over dt they gave us as negative 2 minus 2 times x of 4. dy over dt again is negative 2. All this divided by 2 times the y of positive 2. Okay. So there's just a little bit more algebra to work through, and then we have dx over dt finally worked through. So we can actually start canceling some things out because we have a factor of 2 on both sides, right? So we take out the squared, and then we can take one more factor of 2, so cancel that out. We'll turn this back to a positive by removing that negative there. So we have a positive 6 plus another 4 at the end of all that, so making it a lovely positive 10, right? So dx over dt is equal to 10 units per second. Okay, again, a little bit cramped, a little bit unfortunate that we ended up with that as the end of our page right there, but I think everything there should be good enough for us to get started on grading once we finish problem number 6. Okay, again, this was just a little bit of implicit practice, understanding that by taking a derivative with respect to t across this equation, we have to follow all the rules of differentiation, and remembering to substitute everything back in terms of dy over dx, dy over dt, and such and so forth like that. Okay, let's go finish this off with question number 6, and that will be it for this packet. So let me make sure I turn the page properly here. So we have question number 6 here on this graph here. Let's go ahead and go like this. 1, 2, 3, 4, 5. So we go 5, 10, 15, 20, 25. Up in those marks, then we go 1, 2, 3, 4, 5. Okay. So at x is equal to 2, we have a vertical line right there. And then at x is equal to 5, we have another vertical line right there. Okay. Then we go about and we have these two functions here. Looks like one that curls up like this, and we have another one that kind of dips down and curls up like that. So f of x is the first line, and then g of x is the second line right there. Make sure that's all in frame. Okay. And so we have region R defined right there, and then region S is going to be between those two right there. All right. So let's make sure we have this all colored in quite nicely for us. So region R is this guy right here, and region S, I think I'm going to use this darker color right here. Yeah, so that's region S down there as well. We have two regions which are shaded in right there, and we'll go about this with the context first that f of x is equal to x squared plus 2, and g of x is equal to x squared minus 2x. Okay. So again, R is bound by f of x and g of x. X is equal to 0 and x is equal to 2, those vertical lines. Okay, so then we want to write but do not evaluate. An integral expression that gives the area of region R. Okay, good. So we've gotten another one of these problems that we're writing out, but we are not evaluating. So do not evaluate the integral expression that we need to give the area of R. Again, is that little section of f over g. So f minus g looks like between those two vertical lines of x is 0 and x is equal to 2, right? At the point of 2, we have that vertical line going straight up, and we need to show how we're going to get the area of region R. Okay, so with this, we can conclude that R, again, remember, if we're doing area, it's always remember that it's the integral of the top function minus the bottom function, right? Again, we go in terms of dx because we can take this vertically across the x values on this axis here. So because we're going from 0 to 2 on those x values, that will be our limits. So we go from 0 to 2. And remember, it's going to be, again, the top function minus bottom. If you can see here, curve-wise, f of x is on top of g of x, right? Even though g of x kind of goes underneath the axis, that's still taken account of as a positive value, because by subtracting g of x, that goes back to positive values on that part, okay? So, because of this, we have f of x on the top function minus g of x going in terms of dx. So, if we're going to go ahead and be good students to actually substitute everything in, just so that if we were to put it to calculator, we can get the region of R. We're not going to because this is not a calculator section. They don't want us to evaluate it. But nonetheless, though, we can substitute in for f right here. So it's x squared plus 2 subtracted by all of g of x as x squared minus 2x. Make sure they're in the parentheses, that the entirety of the function is being subtracted. And this is in terms of dx. And that will be how to find the area of region R, just like that. So again, if we had a calculator, we can find it, but we don't, so we're not going to do anything else about it. Okay, then it says here that let S be defined by the region bounded by, let's see, the bounded by G, the x-axis, x is equal to positive 2, and x is equal to positive 5. Okay, so 5 is going to be, and positive 5 is equal to that vertical line going straight up at the end there. Okay, so now they're going to continue, though, that region S is the base of a solid. Okay, right, for this solid, okay, each x, yeah, let's see, yeah, is perpendicular to the x-axis as a rectangle with height equal to the half its base in region X, region S. Okay. Then we want to find the volume of the solid. Okay. And then we need to show all the work. So we actually do need to find the volume, so we'll be evaluating this guy overall. Okay. So the base is in region S of this rectangle. So the idea being that if we were to do this, right, if we were to kind of show this, it's going to be a little bit skewed because we're drawing three-dimensional shapes on a two-dimensional paper. But nonetheless, though, if we had region S a little bit defined like this, right, if that's region S shown right there, again, we have rectangles coming off of this guy, right, like such, like so, again, meaning that the area of that rectangle is going to be the base multiplied by the height. Okay, the base, of course, again, is in region S, right? So the base being that it's going to be g of x on its own, but then the height, though, is going to be height being half of the base, right? So the height being 1/2 of the base, which is already g of x, the actual distance from the x-axis all the way to the top of region S, as shown in that darker section right there, right? Again, this is going to be the distance from g of x all the way to the x-axis as shown right there. Okay, so because of that, we have this area to contend with, but because we are taking this in terms of a volume, that must mean that we take the area and integrate that all the way across. Now, our limits, of course, is going to be from 2 to 5, those two lines which are containing the region of S. So it goes from 2 to 5 of, now, g of x, the base, multiplied by 1/2 times g of x, again, the height in terms of x. Okay, so that's how we get started with the actual volume itself. All right, and then with that, we can go ahead and start plugging this all the way through. So before we go about that, we can go 2 to 5 of 1/2 times g squared of x dx, right? Because it's g of x multiplied by itself. Okay, and then we can then plug in for g of x the equation which was given at the start of the problem of x squared minus 2x for the function of g. So with that, this will be the integral going from 2 to 5 of 1/2 times x squared minus 2x, all that squared dx. Okay, so we actually do need to find the volume of the solid. So it looks like we need to do some integration by hand here. So going from 2 to 5, this will be 1/2 times all of x to the 4th power minus, using FOIL, because again, this entire thing is being squared. So minus 4x to the 2nd power plus 4x squared, and then dx on that side. Okay. So with that, we can go ahead and start integrating this guy across. We can leave that 1/2 coefficient there. Okay. Yes. Well, thank you, Mijini, for coming in into this chat quite nicely, telling that our viewers do need an email if they're looking to get some problems. Yeah. Looks like I already had one coming through today, so we'll be starting to put together hopefully a video for our friend Niraj, who did send one in earlier today. But with that, we are just about finishing up for question number 6. So let's get through this integration and let's see how we can do here. So with this, we can go ahead and take the integration. So it's 1/5 x to the 5th power, right? Then we go subtract it with x to the 3rd power. This will be 4/3 to cancel that out. And then it's going to be, what is happening here? This is supposed to be, it's x to the 3rd power. So that's actually incorrect. Okay, so let's try that again. This is x to the 4th by itself. Yeah, so there's no coefficient there. It's just x to the 4th. That is really messy, so let's try that again. So we're going to do the integration one more time because it looks like I messed up one of the exponents back there. So with the 1/2 coefficient, this is going to be x to the 5th, 1/5, then subtract it with x to the 4th power, okay? And then we add that with x to the 3rd power, 4/3. Okay, so that is the correct integration of what we have inside there. Now we need to run the limits from 2 to 5 for that. Okay, so because of that, we leave the 1/2 coefficient there. Then we start running it through. So it's 1/5, 5 to the 5th power minus, let's see here. So it's x to the 5 to the 4th power, and then 4/3, 5 to the 3rd power. Okay, now all that will be subtracted by the entirety of 1/5, 2 to the 5th power minus 2 to the 4th power plus 4/3, 2 to the 3rd power. Okay, so we have a little bit of work cut out for us because we have 5 to the 5th power and we got a lot of exponents to keep track of. So as a side note here, just so we can keep the numbers consistent, and we know that 5 to the 3rd power is 125. That means 5 to the 4th power is going to be another 5 multiplied into that, so that's 625. And then 5 to the 5th power is multiplied one more time, making it 3125. 3125. Okay, just a little bit of extra notes here just to keep everything in line for what we're doing here. Okay, thankfully though, we actually, because it's 5 to the 5th divided by 5, that can actually take out one variable, so that's 5 to the 4th again. And that's a lot nicer because 5 to the 4th minus a 5 to the 4th is actually just going to go to 0 because of a little bit of simplification done on our side. So with that, our first line of work keeps that 1/2 coefficient there. This is 4/3 5 to the 3rd power, so it's 4/3 times 125. Okay, then we do the subtraction of all of this now, so that's 32/5 minus 2 to the 4th is 16, and 2 to the 3rds with 4/3 is plus a 32/3. Okay, very nice. So we actually have everything to keep this 1/2 to actually distribute all the way across all these guys. So with a bit more simplification, this is going to be 2/3 times 125 minus the 32/5 is 16/5. Then subtracted by a negative 16 is a positive 8. And then subtracted by another 16/3 like this. Okay. Now we just have one last simplifications to go, and we should be just about done here with this part. So the 2 times 125 is 250 right there. And then subtracted by the 16/3 makes it 234/3. Okay, this is actually divisible by 3. That's quite nice. And then we subtract the 16/5 plus the 8. So this guy can actually be simplified into a 78, if I'm correct. 78. So it's 78 plus 8 minus 16/5, giving us an 86. And then we can actually simplify the mixed number for simplification purposes, giving us 82 4/5 as a result of that area. Okay, took a little bit of time just to get everything simplified there, but our work checks out with our integration of such a volume. So with that, that should do it for part B. So let's finish this thing off with part C and we'll see how we go from here. Okay, so with that, we need to write, so part C is saying that we need to write but do not evaluate. An integral expression. That gives the volume of a solid generated when S, that region, is rotated about the horizontal line, y is equal to 20. All right, so we've got ourselves quite a few things going on here because we are rotating about a horizontal line for the region S, but again, we are not evaluating that integral. We just got to write it out. Okay, so with this, we need to make sure that with the horizontal line y is equal to 20, again, we're way up here in this line, right? We can show it in the graph. So it can be a horizontal line y is equal to 20, and then we're rotating about there. All right, because this is the axis of rotation, we need to keep in mind this entire area, right, going from here all the way down to the region S is empty, right? Make sure to keep that in mind. And then we have the entirety of this guy going to the bottom of S, right? So all of this going right in between S and that's going to be full. Okay. Because of this, we need to go about rotating this in terms of a washer here. I think that's the best way of doing it, right? Because we're doing a washer rotation, meaning that the volume with this is going to be described being equal to going from A to B, but now it's going to be it's big R squared minus little r squared dx, because we're still measuring in terms of vertical. Again, dx, we're going all the way across the x-axis to get those limits. Okay, so because of this, we need to then understand what the big R and little r are going to be, right? What are we subtracting from what? Okay, so because we're doing the entire length from 20 all the way down, right? This entire length all the way 20 is going to be the big R. We need to cut away all the empty parts away from it while we're rotating. So because of this, we can then isolate each one. So big R is just equal to 20. That's the whole radius of the entire area that we're looking at. But then little r is going to be the next problem. Because as you can see, we need to just take into account, right, just S being left over in terms of the subtraction. Because of that, little r is actually going to be 20 minus the region of S on that vertical side, which is going to be g of x, right? How does that make sense? Of course, it's by big R being subtracted by little r. As you can see, all that's left over with big R being 20 and little r being 20 minus g of x. By subtracting the two, all that's left over is going to be a positive g of x after doing that subtraction. Of course, those 20s are going to be needed in there because we're scoring the radius and then integrating across, again, as is the washer form of rotation, to find a specific volume of a solid. So because of that, we have looks like everything we need. Again, our limits are going to be well defined from 2 to 5 as are shown on those vertical lines. So with that, we have the entire volume written out here as being equal to the integral going from A to B. So that's going to be from 2 to 5 on the x parts right there. The big R being 20, all that squared, subtracted by little r, which is the distance of 20 taken away from g of x right there, all of that squared dx. Okay, so if we wanted to do this one more step here, just so we know exactly what's going to be put inside of the calculator, that's going to be 2 to 5 of 20 squared minus 20 minus all of g of x, which is x squared minus 2x, all of this squared dx, right? That is what's going to be put into the calculator if we were to do that on our own. But again, this is a non-calculated question. They do not want us to evaluate it. We'll just show it in terms of the integral of that part. All right, so that is actually part 6, finishing up the volume questions here. And with that, we have everything we need here to see what we finally score with our last 2 questions together here. All right, so going back to question 5, the last time that we've graded something, let's switch this on over to the scoring guide so we can go ahead and see how well we've done. So going to question number 5 here, okay, we have on this part here is that, again, we're doing that differential equation with the x and y equation be equal to 48 and that differential equation they started out with. So with part A, right, we're going to use the tangent line to approximate the x-coordinate of 3, starting with the point of 2, 4, right? Because of that, we're supposed to then evaluate at 2, 4 as was shown right there. So we get the slope of -4/19, right? Again, by plugging in the values of x and y right there, -4/19 is going to be slope of the tangent line. That's 1 point scored right there. Okay, and then the approximation does give us 72/19 as a result of plugging that back in for being x is equal to 3 for the tangent line equation. That does match exactly the way that they set it up. So that's going to be 2 out of 2 correct for us on this part A, which is quite nice. Okay, then we can go over to part B here. Okay, so part B is asking if we are dealing with the horizontal line at y is equal to 1 is going to be tangent. So because of that, again, we have to set the differential equation equal to 0, right, in terms of y is equal to 1, right? So because of that, right, we need x then must be equal to 0 for this to be the case, right? The issue, though, is that the point 0, 1, once we plug that right back into the original equation to see if it does line up with the curve, that is simply not the case, right? 3 plus 2 being equal to 5 is not equal to 40 on the other side. Therefore, right, it is the y is equal to 1 horizontal line will not be tangent to the curve on this part of the equation, giving us 2 out of 2 correct for that. Again, for us to determine mathematically why that will not be the case by plugging in for both the slope and then into back to the original equation to see if it was true in the first place. All right, very good. Then moving down to part C here is that we have the intersection at rad 48, 0. Okay, but then we are looking to see if that line tangent is going to be vertical, right? Vertical then meaning that we need an undefined slope, right? Meaning that we need a 0 in the denominator of the differential equation. Okay, but if we actually did plug it in right into with that point of rad 48, 0, we end up with an actual result of -2 rad 48 over 3. Right, the denominator is not 0. That means that the slope of the tangent line is not vertical, and because of that, we have proven that that will not be the case. Right, no, the tangent line to the curve is not vertical at that point of rad 48, 0. And that is a simple 1 out of 1 point here, because it's just really a very simple plug into the differential equation, just so we can prove that the denominator does not go to 0 for that equation. Okay, let's get down to problem D, which is a little bit of a tight fit, but to go over it again, we have a new equation of y's and x's together, which is a particle moving, and at a very specific point at 4, 2, we get the y coordinate decreasing at a rate of 2 units per second, right? So this was going to be the dy over dt. This is the relationship that I pointed out right here, right? So dy over dt, again, a change in y in a change of time in units per second was shown right there. But then they want us to know the change in terms of the x coordinate as well, meaning that they were asking for dx over dt, meaning we had to go back to that equation that they asked for us, take a derivative in respect to d over dt, making sure that it's an implicit differentiation, right? Again, we're leaving things in terms of that coordinate dx over dt for us to solve on its own. Okay, so running the derivative was actually matched up exactly. 3y squared dy over dt plus 2x dy over dt plus 2y dx over dt. And so by isolating it all out, we do end up with dy is a net of 2. Yep, we end up at our last note here is that the answer is that it's going to be positive 10 for the dx over dt, right, by plugging everything else in, by isolating. So with that, that will be everything that they asked for here with that last solution there for 4 over 4 correct on that part. So all of part 5 is going to be correct for us, right? We haven't missed anything there. So that is another 9 out of 9 for us on question number 5. We are on quite the hot streak. So let's go ahead and see if we can finish off question number 6 and if we've gotten everything there as well. Okay, so question number 6 shows us here that we have that graph that we're dealing with f and g as shown right there. So part A is that, again, we are not evaluating, but we want to show the region R is taking its area, which it was very simple, right? Going from 0 to 2 for f of x minus g of x dx. Okay, just top minus bottom to find the integral. And again, by putting that all together, that's going to be 2 out of 2 correct for them to understand what we need to do to find the area of region R as was described in the problem. Okay, going to part B here. This was a little bit of a harder problem, okay? Which, in this case, was that region of S that was bounded between, right, those two. But then again, we have, it's going to be a solid with the perpendicular line to the x-axis, right, which it's going to be a rectangle with the height equal to half for region S, okay? So we then need to understand what that area looks like, which would have been g of x, right, times 1/2 g of x, which in terms of the volume equation, as shown right there, right, be taken as 2 to 5 of 1/2 times gx squared. So all of this, right, does match up exactly. I just plugged in for g of x as you start doing this integration by hand. Okay, so integration limits, again, that this integration all in the inside, and the limits from 2 to 5 are 2 points already scored in for us because we showed that properly. Then moving down, we start doing the integration by hand. It took a little bit of time for us, right, after we did the foiling, and then a little bit of working to make sure the actual running the integral is correct. So it's 1/5 x to the 5th minus x to the 4th plus 4 over 3 x to the 3rd power, evaluated from 2 to 5, as shown in this step right there. That does match, just a little bit different on the positioning, but everything does match exactly the way that they want to. So the actual integration itself is good. And then lastly, running through and plugging everything in and solving everything out. 82 and 4/5, they left it as improper. So if we were to change that back to improper for us, because 82 and 4/5 doesn't match 100%, but 82 times 5 is going to be 410, plus another 4 over 5 gives us that 414 over 5, exactly the way that it should be. I just put it back in terms of a mixed number as it was a little bit easier, but that is 100% the actual exact answer after running the integration. That was going to be the case. That is another lovely 4 to 4 for part B. So let's see if we can finish off with part C and get a perfect score here. So another example of writing but not evaluating the integral expression, where a solid generating around x but is rotated around the horizontal line y is equal to 20, right? So we did show earlier that we are going off the line of y is equal to 20, coming all the way across, and then we're rotating that guy, right, all the way around it. So because of that, our volume will then be the result of, right, the 20 squared minus 20 minus g of x, all that squared, again, the radius of the difference of the two, as shown with the washer rotation form of being able to find solids that way, is big R squared minus little r squared. So it's two different radius as they're being rotated about that axis of rotation. Okay, so because of that, we then can show that it's 20 squared minus 20 minus g of x, and all of that squared as shown. And so we just plug that right into there, as shown on our last bit step there, right, with the limits and the constants all shown properly. So with that, we get 3 out of 3 correct there. That's exactly what they want to see for us to get the right form and the right way of substituting into the problem. So because of that, this is again another 9 out of 9 correct. Quite lovely. Now with that, we have another packet in the books of having a perfect score on this exam. Okay, so I think that's pretty good for what we've done so far. Again, all the steps should have been explained quite well as to what we are looking at and doing. So that is a very lovely perfect score waiting for us, and is now in the books on the 2024 last year's exam for the AP Calculus test. Okay, and so I think that should about do it for today on that matter. Yes, there has been one email that is sent in, a very interesting question on the actual looks like there's some questions that are being sent in by some viewers through the email, the labcoatmath@gmail.com. But nonetheless, though, this entire packet again was done through every single step and with the corrections. So again, I know that there are some people that do look at this VOD after we are done streaming. So again, this is going to be another perfect score exam, which should be gone through with each step. And so with that, that should conclude it for today's live stream. And thank you all for coming in and chatting up to see what we're up to. And hopefully we can see you once again next week as we get into another packet. Right? It is a very good thing to see that, again, there are people interested in what we're doing here. Again, with that AP exams coming within the next month, so I know there's a lot of students kind of rushing in to cram in their last bits of practice, and that's what this whole channel is about at this current time. So, again, thank you once more to everyone that came in to see us, and we'll be back again on Tuesday at 4 p.m. Pacific to then answer another packet of problems. Thank you all, and hope to see you on Tuesday.